Welcome, my friends! In this video, we'll be discussing one of my favorite discrete probability distributions, which is the geometric distribution. The geometric distribution is similar to the binomial distribution, except instead of having a set number of binomial trials, we repeat binomial trials until we get the first success, and then we stop. Let's review the binomial distribution to make sure we are on the same page. Recall that there are 4 features of binomial experiments, which all must be met in order to use the binomial distribution. In a binomial experiment, there are a fixed number of trials where some outcome is observed. Each trial only has 2 possible outcomes, success and failure. Each trial is independent, meaning the outcome on one trial has no impact on the outcome of any other trial. Lastly, the probability of success is the same on each trial. These conditions all need to be met in order to use the binomial distribution. Now, in order to use the geometric distribution, these same 4 conditions must be met, except the first condition must be modified slightly. Instead of a fixed number of trials, the binomial trials are repeated until the first success is observed. In the binomial distribution, we might be flipping a set number of coins, such as 10 coins, and we could calculate the probability some specified number of coins showed up heads. If we were using the geometric distribution, we would continue flipping coins until the first heads was flipped. The number of trials is no longer bounded as it was in the binomial distribution. In the geometric distribution, we just want one success and want to know how many binomial trials it will take until we get that first success. In many real-life situations, the geometric distribution is more appropriate than the binomial distribution. You might only want to roll a die until the first 6 shows up, or you might be a salesperson and only need to call customers until you make the first sale, or you might be contacting lawyers until you find the first one that specializes in a specific area of law that you need. In each case, the geometric distribution might be used to calculate probabilities. The formula used to calculate geometric distribution probabilities is P of x equals P times Q to the x minus 1 power, where P is the probability of success on each binomial trial, Q is the probability of failure on each binomial trial equal to 1 minus P, and x is the number of the trial where the first success occurs, so that x can be equal to the counting numbers, 1, 2, 3, etc. It turns out that for any geometric probability distribution, the mean, or expected value, is 1 divided by p, and the standard deviation is the square root of q over p. To define a geometric distribution, all you need to know is p, and this notation means that x follows a geometric distribution with a probability of success p. Also know that the TI-84 calculator has a PDF and CDF function for the geometric distribution, just like for the binomial distribution, where GeoMet-PDF calculates the probability x is equal to some constant a, and GeoMet-CDF calculates the probability x is less than or equal to some constant a. Let's look at an example. Let's say that a particular box of cereal has a 5% chance of containing a toy rocket. You, of course, decide to continue buying boxes of cereal until you get the toy rocket. If x represents the number of cereal boxes you must open until the first toy rocket is found, then x follows a geometric distribution with a probability of success of 0.05. Recall the formulas for the mean, standard deviation, and p of x in the geometric distribution. Since p is equal to 0.05, q must be 1 minus 0.05, which comes to 0.95. The mean, or expected value of this distribution, is 1 divided by p, or 1 divided by 0.05, which is equal to 20. We expect to have to open 20 boxes on average in order to receive the toy rocket. The standard deviation is the square root of q divided by p, which is the square root of 0.95 divided by 0.05. which is equal to 19.49, a relatively large standard deviation. The formula for probabilities is P of x is equal to P times Q to the x minus 1 power, or in our example, 0.05 times 0.95 to the x minus 1 power. We can use this formula to answer probability questions by plugging in a value for x. For example, what is the probability that we find the first rocket in the first box of cereal? That's the probability x is equal to 1, so plug in x equals 1 into the formula. 0.05 times 0.95 to the 1 minus 1 power, which simplifies to 0.05 times 0.95 to the 0th power, which is equal to just 0.05. There is a 0.05, or 5% chance, that we find the rocket in the first box of cereal. This shouldn't be too surprising. What is the probability that we find the first rocket in the second box of cereal? Well, that's just the probability x is equal to 2, so plug in x equals 2 into the formula. 0.05 times 0.95 to the 2 minus 1 power simplifies to 0.05 times 0.95, which is equal to 0.0475. There is a 4.75% chance that the first toy is found in the second box. For finding the first rocket in the third box, we use the same process to get 0.045125. If you look closer at the formula, you can start to understand what the math is doing. For the probability x is equal to 3, that means that the first success occurs on the third trial. Therefore, we have 1 success and 2 failures, which is reflected in the formula. 0.05 times 0.95 squared. For x equals 2, the first success occurs on the second trial. Therefore, we have 1 success and 1 failure, which is reflected in the formula. 0.05 times 0.95. If you'd rather not use the formula, you can use the geomet PDF function on the TI-84 calculator to find the same probabilities. Press second, vars, scroll up to get to the bottom of the list, and select geomet PDF. For p, type 0.05, and for x, type 1. You will get 0.05, just like we got in the formula. If you press second, enter, you can bring up the formula again. Change 1 to 2. We get 0.0475, just like before. Pressing second, enter again, we can change 2 to 3 to get 0.045125. Suppose you purchase 3 boxes of cereal. You get lucky and find the toy rocket in the third box. What is the probability of finding a toy rocket in one of the first 3 boxes of cereal? Well, in the probability statement, we have the probability x is less than or equal to 3. One way to solve for this would be to add up the 3 probabilities we already calculated. The probability x equals 1, 2, or 3. Remember that x equals 0 is not a possible outcome, because that would mean getting the first rocket toy before you even opened any boxes. The geometric distribution always starts at 1. Okay, so we have 0.05 plus 0.0475 plus 0.045125, which equals approximately 0.1426 or 14.26%. These are just the probabilities we calculated earlier from the previous slide. There is a 14.26% chance that the first toy rocket will be found in one of the first 3 boxes opened. Alternatively, you can use the geomet CDF function to solve for less than or equal to probabilities like this one. Press second, distribution, scroll up, and select geomet CDF. Enter p equals 0.05 and x equals 3. Paste and press enter, and you should get the same answer. Let's say you really want this toy rocket, but you don't want to have to buy more than 30 boxes of cereal to get it. What is the probability you will have to buy more than 30 boxes of cereal to get the toy rocket? Well, that's just the probability that x is greater than 30. Now, this is one you can't do with the formula. There are an infinite number of outcomes greater than 30 that are all possible. The first toy could be found on box 31, on box 32, on box 100, on box 1 million. Any number is possible, even if some of them are very unlikely. Our calculator functions only calculate either equal to probabilities, in the case of geomet PDF, and less than or equal to probabilities, in the case of geomet CDF. How might we solve this problem? Well, the easiest way is just to use the complement rule. The complement rule says that we can take 1, which represents 100% or all of the outcomes, and subtract the outcomes in the complement, the outcomes not included in our probability statement. We will be left with the probability of the outcomes that we do want to solve for. Using the complement rule, the probability x is greater than 30 is just 1 minus the probability x is less than or equal to 30. We could calculate the probability x is less than or equal to 30 with the formula, but that would be 30 calculations that we'd have to add together. The geomet CDF function is much more efficient, so that's what we will be using. Our answer is 1 minus geomet CDF 0.05, 30, which is equal to 0.2146 or 21.46%. There is a 21.46% chance that you will have to buy more than 30 boxes of cereal in order to get the toy rocket. Something I have always found fascinating about the geometric distribution is that the majority of the time, the first success will occur before the expected value. In our case, we might ask what the probability is that we receive the first toy rocket by the time the number of cereal boxes opened reaches the expected value. Recall that the mean, or expected value, is just 1 divided by p, or in our case, 1 divided by 0.05, or 20. The fraction form of 0.05 is 1 over 20, which tells us that there is a 1 in 20 chance of getting the toy rocket in any single box of cereal. If you were to purchase 20 boxes of cereal, you might be tempted to think that there is a 50-50 chance of receiving the toy rocket. But it turns out the odds are in your favor. Your chances of receiving the toy are greater than 50%, typically somewhere in the low to mid 60%, depending on the exact value of p. In our example, the probability you find a toy rocket in one of the first 20 boxes is the probability x is less than or equal to 20, which is geomet CDF 0.05, 20, or 0.6415. Even though there is a 1 in 20 chance of receiving the rocket in each box, there is a greater than 50% chance, a 64.15% chance to be exact, to receive at least one rocket if 20 boxes are opened, which is something that I find fascinating. Alright, my friends, that wraps up our discussion of the geometric distribution. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.